Welcome to This Explainer. You know, if you've ever stopped to wonder what actually keeps the salt on your table solid or the water in your glass liquid, the answer literally comes down to microscopic handshakes between atoms. Today, we're stripping away the jargon and looking at the absolute nuts and bolts of how our universe is built. We are diving into chemical bonding. In This Explainer, we're going to do a no-nonsense breakdown of these interactions. No time pass, just the fundamental mechanics of how atoms achieve stability. Okay, let's dive right into this.
Here's the game plan for today. We'll cover the quest for stability, ionic bonds, covalent bonds, coordinate bonds, and finally, how to compare compound properties. Let's get into it.
All right, kicking things off with Section 1, the quest for stability.
It's literally the most fundamental question in all of chemistry, right? Why do atoms even bother combining in the first place? Why can't they just chill perfectly well on their own? The answer is shockingly simple, but it dictates literally every chemical reaction in existence.
Okay, so take a look at the noble gases. Helium, neon, argon, the whole VIP club of the periodic table. They're the chemical elite. And if you look closely at their electronic configuration, there's a very obvious pattern. Except for helium, which rocks a perfect duplet of 2 electrons, every single one of these inert gases has exactly 8 electrons in its outermost shell, an octet. In the atomic world, having 8 outer electrons is like reaching nirvana. It represents perfect stability. Elements that don't have this, they're restless. They are highly reactive, constantly out there hustling, trying to combine and swap electrons just to mimic that perfectly stable, unreactive noble gas state. This deep-seated drive to reach a duplet or an octet is the single underlying cause of all chemical combinations.
Moving right along to Section 2, ionic bonds, where we're transferring electrons.
So what's the first major strategy atoms use to hit that magic number? Well, an electrovalent or ionic bond is basically nature's most straightforward transaction. It happens when electrons are completely handed over from one atom to another. Imagine a metallic atom just tossing away an electron. When it does that, it becomes a positively charged ion known as a cation. And the non-metallic atom that catches that electron, it becomes a negatively charged ion, an anion. Because they now have opposite electrical charges, they are pulled together by a massive electrostatic force of attraction. That invisible, powerful grip, that is your ionic bond.
But you know, they don't just hand over electrons randomly. Specific conditions absolutely have to be met. For an ionic bond to form, one atom has to be highly electropositive. That means it has a low ionization potential. It's super willing to let its valence electrons go. We're usually talking about metals from groups 1, 2, or 13. Now, the other atom needs a high electron affinity. It really wants to pull an electron in. This is typically a nonmetal from groups 15, 16, or 17. So the bottom line here is you need a really large difference in electronegativity between the two elements. The bigger that difference, the smoother the transfer, and the stronger the ionic nature of the resulting compound is going to be.
To put that into perspective, let's look at a classic transaction. Check out the orbit structure of sodium chloride, basically just regular table salt. We have the sodium atom. Its configuration is 281. It's got this one incredibly vulnerable electron hanging out in its outermost shell. Then you have chlorine, sitting at 287. It is agonizingly close, just one single electron short of a perfect argon configuration. So sodium completely offloads that outer electron to chlorine. Bam! Sodium drops to a super stable 2,8 configuration, just like neon. Chlorine bumps up to a perfect 288, matching argon. They both get exactly what they want, and that resulting electrostatic pull locks them into a deeply stable ionic compound. It's a total win-win.
All right, Section 3, covalent bonds and the art of sharing electrons. So what happens when 2 atoms meet up and neither one wants to give up an electron? Nobody's budging. Enter the covalent or molecular bond. This is formed through the mutual sharing of one or more pairs of electrons. And mutual is the absolutely crucial word here. Since nobody is fully gaining or losing an electron entirely, you don't get any charged ions forming. Instead, it's a partnership. They pool their resources, sharing those valence electrons right in the space between them, allowing both atoms to simultaneously count those shared electrons toward their own octet or duplet.
Now, the conditions for this setup are the total opposite of what we just saw with ionic bonds. Covalent bonds form between atoms that both have crazy high ionization energy, meaning losing an electron would require way too much energy. Plus, they both have high electron affinity. Because both atoms are playing tug-of-war and attracting electrons really strongly, the difference in electronegativity between them is basically zero, or totally negligible. This is exactly why nonmetals, like hydrogen teaming up with chlorine or oxygen mixing with carbon, rely on covalent bonds.
They can't overpower each other, so they are literally forced to compromise and share.
But let's be real, sharing isn't always fair, right? Let's compare two different molecules to see how this plays out. Take methane. You've got one carbon atom sharing electrons with 4 hydrogen atoms. Because they have almost identical electronegativity, those electron pairs sit perfectly dead center. It is perfectly symmetrical, entirely neutral. That's a nonpolar covalent compound. But then look at water. Oxygen is significantly more electronegative than hydrogen. It's a bit greedy, to be honest. It hogs those shared electrons, pulling them closer to its own nucleus. Because of that unequal sharing, the oxygen end gets a fractional negative charge, and the hydrogens get a fractional positive charge. That charge separation creates what we call a polar covalent bond. It's technically sharing, but one side is definitely getting the better deal.
Which brings us to Section 4, coordinate bonds and the magic of the lone pair.
Okay, so here's a really fascinating twist on the sharing model, the one-sided share. It's called a coordinate or dative bond. It is technically a covalent bond because, yes, it relies on a shared pair of electrons. But the huge kicker here is that this shared pair is provided 100% by just one of the atoms. One atom steps up as the generous donor, offering up a lone pair, which is basically a pair of electrons that isn't currently doing anything else. The other atom is completely strapped for electrons and acts simply as the acceptor. But the crazy thing is, once they make that connection, it behaves exactly like a normal everyday covalent bond. A perfect example of this is the formation of the ammonium ion. Think about a standard ammonia molecule. The nitrogen atom has already made 3 perfectly normal covalent bonds with 3 hydrogens. But crucially, it has this one unshared lone pair of electrons just hanging out at the top. Then a rogue hydrogen ion floats by, a proton with literally 0 electrons. Nitrogen swoops in, donates its lone pair right into the empty space of that hydrogen ion. Now they share it. Nitrogen is the donor, hydrogen is the acceptor. And the whole structure becomes the positively charged ammonium ion. It is just an absolutely brilliant chemical workaround.
All right, final stretch. Section 5, comparing compound properties.
So this is where all this microscopic theory actually hits the real macroscopic world we can measure. Let's compare boiling and melting points. Remember how ionic or electrovalent compounds are locked together by those incredibly massive electrostatic forces between oppositely charged ions? Breaking those bonds takes a staggering amount of thermal energy. That is exactly why ionic compounds, like your everyday table salt, are hard, non-volatile solids with incredibly high melting and boiling points. Covalent compounds, on the other hand, exist as individual distinct molecules. Sure, the bond inside the molecule itself is strong, but the actual forces holding the different molecules to each other? Super weak. Because of that, it takes very little energy to pull them apart, making covalent compounds highly volatile. They're usually liquids or gases with really low melting and boiling points.
And what about electrical conductivity? Well, to run a current, you need mobile charges. In their solid state, ionic compounds actually can't conduct electricity because all their ions are locked tightly into place. But melt them down or dissolve them in water and everything changes. Those electrostatic forces weaken, the ions dissociate and start moving around freely, and boom, they become fantastic conductors. Covalent compounds, conversely, are made of neutral molecules, not charged ions. Because they have no free ions to carry a current, they are pretty much pure non-conductors. But, and there's always a but in chemistry, remember those polar covalent molecules we looked at earlier? If you drop something like hydrogen chloride into water, the water molecules can actually force it to ionize, creating free ions that suddenly will conduct electricity. Nature always finds a loophole.
So, as we wrap up this explainer, I want to leave you with this thought. The structure of matter isn't magic. It's a deeply logical system of transactions and partnerships, all driven by this universal pursuit of stability. Take a look around you right now. The solid metal of your desk lamp, the liquid water in your glass, the invisible oxygen gas you are breathing right this second. What unseen atomic bonds, whether they are strict ionic transactions or shared covalent partnerships, are holding the very objects in your room together at this exact moment? Take a closer look at your physical world today and see if you can decode the architecture of matter hidden just beneath the surface. Thanks for joining me on this explainer, and keep questioning the mechanics of the universe.